Hello dear students. Actually today we are going to start with a topic PN junction. As we all know that we have already studied how the p-type semiconductor is formed, how n-type semiconductor is formed. Whenever trivalent impurity is added in pure semiconductor, then p-type semiconductor is formed. That already you are knowing. Whenever pentavalent impurity is added in pure semiconductor, then n-type semiconductor is formed. We have already studied all these things. So today we are going to start with a new topic, that this p-type semiconductor is joined with another n-type semiconductor, and then it will be formed as PN junction. And this particular device we are going to study here, which is having lots of application in the field of electronics. Actually, these are the topics we are going to cover it today regarding this PN junction diode. Introduction, after that unbiased PN junction diode, and these are not many topics. One by one we will cover it up. So let us start with PN junction diode introduction. I already told you that how intrinsic semiconductor is there, how extrinsic semiconductor after doping we form, and then we are going to form a PN junction diode whenever p-type semiconductor, look at to this, whenever p-type semiconductor is joined with n-type semiconductor, then of course it is going to be a beautiful device which can be used as a switch in case of rectifiers. It can also be used in many of the applications. This is actually the symbol of this PN junction diode, and this looks like this. Whenever you purchase this PN junction diode, then it will be looking like this. In the symbol, a beautiful feature is there. Look at to this, how the symbol is to be recalled, how the terminals are to be known. Look at to this, that this vertical line that always indicates negative terminal, and rest of the other terminal that will of course be the positive terminal. It is having two terminals, one drawn from p-type semiconductor, another drawn from n-type semiconductor. In this way we can say that PN junction diode, it is having two layers as well as two terminals drawn from each layer. Now, after formation of this PN junction diode, look at the beauty of this PN junction diode, that how it can be used. It can be used in two ways. It can be used in forward bias, it can be used in reverse bias, but initially we are going to study the unbiased PN junction diode. We are not going to give any biasing to this PN junction diode. We are not going to apply any external potential to this PN junction diode. We are simply studying the unbiased, without any biasing, how this PN junction diode is going to behave. Now let us see. Whenever p-type semiconductor is joined with n-type semiconductor with the help of certain process, that process is known as diffusion process. Dear students, this diffusion process, in this diffusion process, that is activated in the middle part of this P and N region, and it will form a junction, and near this junction some of the electrons from this n-type semiconductor, of course free electrons, because in n-type semiconductor, if we are saying that n-type semiconductor is there, then definitely there are large number of free electrons available. In p-type semiconductor, absolutely there are large number of holes available, and these p-type and n-type semiconductor are when joined together, then at that time, during this region, look at to this, during this region, what happens, that extra, that is free electrons, these free electrons will try to move to the p-type semiconductor, and they will try to recombine with the holes of the p-type semiconductor at the edge. In the same way, the holes of this p-type semiconductor will move to the n-type semiconductor, and they will again recombine. But this will happen only near the junction. Later on, the n-type semiconductor electrons cannot go to the p-type semiconductor because there is a layer of n-type semiconductor, and of course there will be a big or huge repulsion, and that's why these n-type semiconductor, further n-type semiconductor cannot reach here in p-type. In the same way, these holes cannot reach to the n-type just because that there is a layer of these p holes, positive charges, and there will be huge repulsion in that. In this way, this particular region will be a depleted region. My dear students, this will be a depleted region. Because of this particular region, further recombination is not possible. And now, after that, how much is this particular depletion? Depletion means what? Depletion means barrier. Depletion means barrier. Because of this barrier, there is not possible, there is no recombination, further recombination which is possible. Not possible at all. And now, if we want to use this particular diode in the electronic applications, then we will have to start this device. We will have to start this device. And if we want to start this device, then anyway, for the current to flow from P-type to N-type or N-type to P-type, you can say, that particular charge carriers must reach from one end to another. And when this is possible? Because now there is a barrier. How it is possible? So in that case, what we will do? We will apply external potential. So external potential we are going to apply here. Now see how the external potential is applied. External potential that can be applied in two different ways. Out of that, the first way is forward biased PN junction. Means what? We are going to apply this external potential which will be increasing the strength of these charge carriers. See, positive, here negative. P-type semiconductor, that is anode. We are applying this anode terminal to the positive of battery. We are applying this cathode terminal to the negative of battery. What does it mean? It means that we are providing more positive energy to these holes. We are providing more negative energy to these electrons. Isn't it? Now, what will happen? If more energy is provided to the electrons, electrons will be more excited. They will try to reach to this one. But one thing must be taken care, that for the silicon diode, for the silicon material diode, this depletion region is of 0.7 volt. And for the germanium diode, this depletion region, of course, it is 0.3 volt. So, how much potential we will have to apply here? We will have to apply a potential which will be, of course, more than this depletion region. Then only it is possible that these charge carriers will reach from this end to this end and holes will reach from this end to this end. And therefore in forward biasing, since such type of biasing we are providing, the current is easily possible after the application of simply 0.7 volt or more than that. And this is what is called as forward biasing. In the same way, we can study reverse biasing also. But in reverse bias, one thing must be clear, that in forward biasing we haven't considered the minority charge carrier. But in reverse bias, we will have to consider that. Why? The reason behind that is, whenever we are providing reverse biasing, what does it mean? We are compelling the charge carriers to attract to that particular end. See, negative terminal is applied to the anode terminal where very nearby holes are there, that is positive charges are there, and positive terminal is applied to the cathode. What does it mean? What will happen with this? With this, it is going to happen that these holes in P-type semiconductor, that those will be attracted to this negative terminal, because negative terminal you have applied, and the electrons, those will be attracted to this positive terminal. What will happen with this? All the holes will be moving towards the negative terminal. All the electrons will be moving towards the positive terminal, and in between there will be a space generated, huge barrier that will be generated. In this way we can say that the depletion region that is going to be increased. And if the depletion region is increased, how come these majority charge carriers, that is holes in P-type and electrons in N-type, how can these charge carriers will move? How can these charge carriers will recombine and current will flow? Hence we can here conclude that because of majority charge carriers, it is not possible that current will flow here. But one thing I have already told you, that we have to consider minority charge carriers also. Now, if we apply reverse biasing, minority charge carriers in P-type semiconductor, which will be the minority charge carriers? Of course, electrons. Which will be minority charge carriers in N-type semiconductor? Of course, holes. For these electrons and holes, which are minority in P-type and N-type, for them, the applied potential will just be a forward biasing. Just like a forward biasing, and here, as and when we increase this potential, the charges or the energy of these minority charge carriers will increase. And what they will do? They will start recombining, not only start to recombine, but they will break another covalent bonds also. They will break another covalent bonds, and in this way, these covalent bonds, because of the breaking of these covalent bonds, the number of electrons and number of minority holes that will be increased, and one time will reach that heavy current that will be flowing through this device, which is known as breakdown voltage. And with this particular voltage, it is possible that this junction region that will be scratched up, that will be distracted, that will be damaged. And this particular voltage therefore is told as avalanche breakdown. Dear students, with this